Hello everyone. In this video, we will be talking about heat pumps. Heat pumps are an application of the second half of the second law of thermodynamics, which stated that heat does not spontaneously flow from a low temperature environment to a high temperature environment. So, since the energy won't flow from a low temperature to a high temperature environment spontaneously, we can input energy to make the reaction go in the opposite direction. So we can do work on the system to cause it to flow towards the high temperature environment. To see how well a heat pump performs, we use the coefficient of performance, which is the heat flowing out of the low temperature environment over the difference of the heat flowing into the high temperature environment and the low temperature environment, or QL over the work we do on the system. Typically, the coefficient of performance should be above 1 for it to be a heat pump. Much like the Carnot engine, there is an ideal coefficient of performance as well for this kind of system where the reaction could be reversible. For ideal, we again use the temperature for the low environment over temperature of high environment minus the temperature of the low environment, which would give us the ideal coefficient of performance for a given heat pump. Let's look at an example problem. Let's say we have a heat pump with the coefficient of performance of 3, and it is rated at 1,000 watts. We want to know what the heat going into the high temperature environment is and the heat coming out of our low temperature environment for this particular setting per second. Now, if you cast your mind back, we know that power, which we see as watts, is energy over time. So per second, we are expending 1,000 joules of work. So we know from the equation here that our low temperature environment heat would be the product of the work done and the coefficient of performance. And for this product of 1,000 joules and 3 for our coefficient of performance, we would have the heat that exits our low temperature environment as 3,000 joules. Now to see the heat that enters our high temperature environment, we know that QH will be the sum of our low temperature environment heat that comes out and the work we put into the system. Which will be 3,000 joules plus 1,000 joules, giving us an energy of 4,000 joules entering our high temperature environment. Thank you for watching, and see you for the next video. I hope you found this video really helpful. The concepts and information presented in these videos will be true no matter what physics class you are taking. However, the concepts presented in this video are referencing material currently covered in Baylor University's coursework. Remember, if you are a currently enrolled Baylor student, we offer free tutoring services. Our tutoring center is located on the first floor of the Sid Richardson building. You will find all the details you need about these services on our website at www.baylor.edu/tutoring. You may schedule a free 30-minute one-on-one tutoring session online, or just drop in during any of our open business hours. For more information about our current services, please visit our website. Thank you.